So today we're going to be working on graphing on the number line, and we're going to be doing what we call single variable inequalities, which means I only have one letter or one unknown value in each of these inequalities that I'm going to be graphing on which side can I plot numbers and make a true statement. And what I mean is that when I plug numbers in for my unknown value, does it make it a true statement? And so we always shade with truth. We leave blank false statements. Leave blank the false. So that's going to be the general rule of which we do things through. So anything that is true means it makes a true statement. The other thing that we're going to have to realize is that this inequality symbol always opens towards the larger value. So it can be read either left to right or right to left. It always opens towards the larger value. One of the big things that we see in early math is that students are either taught or they learn that this is a greater than symbol and only a greater than symbol. That's not exactly true because in this case it's opening towards the larger of the two. X is greater than 3 because it's opening towards x. But from the 3's perspective, 3 is less than x. So it's not a greater than or less than specifically, it just tells us which one is bigger, and it opens towards the larger of the two. So with number 1, we're looking at some values that are larger than 3. So on our number line, what we're going to do is we're going to put 3 right at the very center. And I need some numbers to the right, so 4 and 5, 2 and 1. And because I'm dealing with 3 specifically, I'm going to circle the spot on the number line, and we're going to come back to that. Now, I'm going to plug in values that are greater than 3 are the only values I can do. So I'm going to ask myself, is 5 greater than 3? If I plug my 5 in where my x is? The answer is yes. So this is true, which means that portion of the graph we are going to shade in, and the way we shade it in is we thicken the line. So I know that the 5 is greater than 3. I could also plug in the 4, 4.5, 3.1, 3.001. Anything on this side of the line is true. Unlike if I plug in things on this side of the line, 1 is not greater than 3. This is false, which means I do not shade the left part of the line. The last part that I look at is I try my point. So I ask, is 3 greater than 3? That is also false. It is equal to 3 but not larger. So I leave my circle open. And so that is all we're doing. If I'm looking at number 3, I know I have a value. This time I'm going to plug it below the line, give us a little bit more room on top, of a negative 1. And I need some numbers to the right of negative 1, 0, 1, 2. I need some numbers to the left, 2, 3, and negative 4. I'm going to draw an open circle on my negative 1 because that's an important point. And I'm going to try out some values. I'm going to plug in a 2. I'm going to plug in a negative 4. And if I plug in a negative 4, I'm going to ask myself, is negative 4 less than negative 1? Or is negative 1 larger than negative 4? Likewise over here, I'm going to say, is 2 less than negative 1? Or is negative 1 greater than 2? We know negative 1 is not greater than 2. It's actually farther to the left on the number line, which means this is a false statement. Negative 4 is less than negative 1. This is a true statement, which means I'm going to shade in the side of truth, which means any of these answers over here are also true. The last thing I try is I try the original value, and I say, hey, is negative 1 less than negative 1? And the answer is no. This is a false statement, which means I leave my circle open. What we're going to see on these two is I'm looking at y, any values, any guesses to plug in that are greater than or equal to my number. So you probably already notice where this is going. If I plug in an 11, 12, a 13, 10, and a 9. Now I don't need to fill up the whole number line specifically, but I do need to give it some context. These are the lesser numbers, these are the greater numbers. The number line goes up, the number line goes down. So if I put a point at 11, I'm going to try out some number over here, some number over here, and I'm going to plug in my original value. So I need the ability to plug in 3 values. The first one I'm going to plug in is 9. Is 9 greater than or equal to 11? The answer is no, this is false, which means I do not shade over there. Do I shade on the other side? Well, let's try a number. Is 13 greater than or equal to 11? Yes, which means I do shade this side of the line. And the last number that we plug in is going to be the actual point itself. So I'm going to ask, is 11 greater than or equal to 11? And it is, it's equal to it. So I know that this is true, which means I take my original point and I shade it in. That's all we're doing. The same with 8. I plug in my 8, 9, 10, 7, 6. Fill in my point. I'm going to plug in 3 values. Some number off to the right. Doesn't necessarily need to be right here. I could plug in a number farther up. I could say 20. Likewise, I could plug in a number farther to the left. 0, which is over here somewhere. And then I'll plug in my main point. I know that 0 is less than 8. 20 is not. And 8 isn't less than, but it's equal to 8, which makes this true. So I have true on the left, which means I shade in on the left. The middle is true, which means I shade in my point. This is false, I do not shade to the right. And that's all we're doing. For some of the later ones, we're simply taking the equation and we're going to work it out a little bit, or in this case, the inequality. X is greater than some value. I have to do something before I can figure that out. So I'm going to take 11 and add it to 5. X is greater than 16. I'm going to take my values on my number line. 16, 17, 18, 15, and 14. I'm going to put an open circle on 16, and I'm going to see 3 times. Is this greater than 16? Is this greater than 16? Or is this greater than 16? So some number to the right, like we did way over here on the last one. So let's do another one way over here. Let's say 100, which should be way off the paper. I'm going to pick a number way over here again. I'm going to pick 0, and then I pick the number itself. I'm going to go through. 0 is not greater than 16. That is false. 16, it's equal to, so it's not greater than 16. So this is false. I know 100 is. And so that means that I do not shade to the left. I do not shade my point, but I do shade to the right. And so we see that these style inequalities are no different than what we had up top. We just have to do a small bit of math before we can get to our answers. R is less than because it's opening towards this bigger number. So whatever 7 times 8 is, which is 56, 56 is greater than R. R is less than 56. That's what we're graphing. So I'm going to put my 56 in the middle, 57, 55. I space them out a little bit more. There's no need to put them one apart. If you don't like that, we can set whatever scale we want. As long as my numbers on the right, on the number line, are to the right, my numbers that are lower are to the left. I'm going to try 3 values. I'm going to try some number to the left. Let's try 55 and a half. So 55.5. We'll try 56. Let's try 56.5. Getting really close to this circle right here. Well, I know 56.5 is not less than 56. 56 is not bigger than that, so that is false. A number is not less than itself. That is false. I do know that this left one is true. 55.5 is a smaller number than 56, which means that, again, we shade the side of truth. So I'm going to shade over here. What we do right here, remember, anytime we see parentheses, that means multiplication. Same as what we did up here. It's another way of seeing it. Y is greater than or equal to 40. Plug my 3 values. 40, let's say 41, let's say 39. Open circle. 40, 40, 40. I'm going to plug in these numbers this time. 39, 41, and 40. Now remember, with the bar beneath it, that means we also have the option of or equal to. So I look at 39 is not less than 40. 40 is equal to 40. That is a true statement. And 41 is larger than 40. Which means that as we shade it in, I know I have truth at my point. I could plug that in. I have truth off to the right. And no truth on the left. Number 15, we reduce by division. I plug in my point of 4, 5, 3. I know that my value at 4, less than or equal to 4, less than or equal to 4, less than or equal to 4. So we're going to pick whatever number we like. I could pick 5, I could pick 6, I could pick 7. Over here I could pick 3, 2, or 1. In the middle I always pick my number. And I see, okay, 1 is less than 4, that's true. 4 isn't less than, but it is equal to, so that's also true. 7 is not, that is false. And so I shade to the left because the left is true. I could plug in any one of those values and be correct. And I could fill in the middle because I could plug 4 into this equation and it still be correct. The last thing is a little bit more of an advanced topic. Here we have a variable on both sides. So if I have a 2x on the left, an x on the right, we're going to cover this more often in the future. So at this point, all you need to know is what's above. We're going to come back to this, so you're welcome to pause and continue on. If not, I'm going to walk through these here in just a moment for those of you who need a little bit more of a challenge. So let's take a look. When I have a variable on both sides of the equation, I need to move that x over here. And now I'm going to look at this as there's a bar between the two values. If I move the x over there, I have to take it away on the right-hand side. And take away, we know, is represented by subtraction. If I take something away on the right, in order to be fair, I have to take it away on the left. So x take away x is nothing. It's just a -1. 2x take away x, well, it's 2 take away 1 is just 1. So I'm looking at values that are less than -1. So -1, 0, -2. I'm going to draw my point. less than negative 1, less than negative 1, less than negative 1. Plug in 3 values. Let's plug in those. Negative 2, negative 1, 0. Well, I know 0 is not less than negative 1. I know negative 1 is not less than itself. I do know negative 2 is less than negative 1. It's farther to the left. Which means I don't shade the right, I don't shade my point, I only shade to the left on the number line. And this last one is probably the hardest one that we'll see for a while. If I have 4y on the left and 2y on the right, just like what we did up there, I want to take away that x to move it over. I want to take away both those y's. So if I take away 2 on the right, I take away 2 on the left, and then I'm even on both sides of the inequality. If I have 2 y's and I take them both away, they both go away. So now I'm left with 2y is greater than or equal to 8. 4 minus 2 is 2. Now, if I have 2 pencils that are worth more than or at least $8, how much is each pencil worth? $4. How'd you get that? Well, you said, well, if 2 pencils are worth 8, half of that would be a single pencil, and half of that would be $4. What exactly did you do? Well, you divided. You said, I'm dividing this by 2 and that by 2. Again, we keep it even. What we do on one side, we do on the other side. So we're left with y is greater than or equal to 4. 4, 5, 6, 3, 2. Open circle. And I'm going to try out 3 values. Greater than or equal to 4, greater than or equal to 4, greater than or equal to 4. I plug in a 2, I'll plug in a 4, I'll plug in a 6. That's true. 6 is bigger than 4. That's true. 4 isn't bigger than 4, but it's equal to. And then this is not. So according to this rule, I shade my point, I shade my right, and I do not shade my left. And there we go. That's how we graph on a number line.
So today we're going to be graphing intersections and unions, or what we call compound inequalities. So what an intersection is what we call an AND function, or it's denoted by what looks like an upside down U. And this is where the portions of 2 different number lines overlap or shared values. A union is where we plug them together. It's represented by an OR function, or a U, and it's the combination of 2 different number lines where we include everything. And many of you might be looking at this saying, hey, I don't necessarily understand what this means, but you've been doing problems like this for a very long time. Let's take a look at one example of an intersection and a union. And this is a perfect example. We all know what this is. This is a Venn diagram. So let's look at a Venn diagram between tigers and sharks. Well, first off, we know tigers have hair. They also have legs, and they live on land. We know sharks have fins, they live in the sea, and they swim. Well, actually, tigers swim very well as well. So, a couple different things. We notice they both swim. They both have sharp teeth. And they both eat meat. We also know that neither one of these tigers nor sharks is a planet, because that's just silly. So tigers nor sharks are a planet. So let's take a look at what we have here. We notice that our intersection, where our graphs intersect, right here, they both eat meat, they both have shark teeth. The 2 graphs literally overlap. This is our intersection. If I were to make a list of where the graphs intersect, swimming, sharp teeth, and eating meat would be the list. So our intersection is right there. By comparison, if I were to list everything, meaning if I were to unionize these two graphs and include everything that they both have, I would list hair, legs, land, fin, sea, they swim, sharp teeth, and eat meat. Doesn't matter if the tiger has it, the shark has it, they both have it. The only thing that's not included on the part of the union is what they're not. They're not a planet, because that's silly. So let's take a look at a few of these, thinking of the Venn diagram in mind. So our first example is we have x is less than 3, x is greater than 0. So I know that I need a couple different numbers on this graph. I know I need a 0, so I'm going to put 0 on both of them, and I'm going to count up till 3. So I have a 3 right there. So in between both my graphs, 4, 5, 6. So now I have 0 and 3 on both my graphs. I'm going to graph my x is less than 3 on the first one. So I'm going to put an open circle on 3 because 3 is not included. And I'm looking for values less than 3 because it's opening away from my variable. 4 is not less than 3, but 2 is. So I'm going to shade the portion of my graph over here with the 2. On the next graph, I'm going to say, okay, cool. X is greater than 0. So I'm going to put a circle on my 0 and say, I'm looking for numbers bigger than 0. 1 is, -1 isn't. So what I'm going to do is shade the part where it has numbers greater than 0. And now here's where we have unions and intersections, where we have and or ors and ands. So let's see what an or function looks like. A union says I can have either this graph or this graph. So a trick that I like to do is I like to draw a dotted line from the first border and the other border all the way down onto my graph so that I can visually look at what's going on. And we'll see why here in just a moment. Because it's going to be the same numbers. I'm going to have a 0 here, a 3 here, a 0 here, and a 3 here. I'm going to have all the same numbers, -3, -2, -1. I'm going to have 1 and 2 in the middle, and 4, 5, and 6 on the right. And so what we're going to have to ask ourselves is, with a union says all values included. Remember, the union was any possible trait in our Venn diagram. So if I look at both these graphs, does one of the graphs have a -3 on it? Yes, the top one does. So guess what? I'm including -3. Does one of them have -2? The top one. Does one of them have -1? The top one. Does one of them have 0? The top one. They both have 1. They both have 2. The bottom one has 3, 4, 5, and 6. And so we can go through and say the top one has these values between. And the top one has these values. They both have all of these values. And then the bottom one has all of these values down here. So what we've noticed is that we've actually filled up the entire number line. So a union of these two graphs is all real numbers. That looks like an 8. Or infinite solutions. That one worked pretty well. But let's try an intersection now. Only the portion where they overlap in the middle. So in this case, where do they overlap? Well, if I look on the left, only one of them has the value of -3. So I'm not going to put it. Only one of them has the value of -2. Only one of them has the value of -1. They both, however, have the value of 1 and the value of 2. And everything in between And as we move farther out to the right, only the bottom one has the 4, the 5, and the 6, so I can't include those. And so because this has areas that are not included, I need to put boundaries so that I know, okay, I'm shading all the way up to here and all the way up to here. And then I have to ask myself, is my 0 in both my graphs? Well, definitely in my top, but on my second graph, it's not included. So I can't include it in my intersection. It's just the barrier. It's just the boundary. The same goes for 3, except for in reverse. It's included in the second graph, but not in the first. So it exists as a boundary, but it's not included. So there we go. There's our intersection from 0 to 3. Now this is just a graphical way of showing these. We will later on go into interval notation and list the actual numbers in both these. But as of right now, we're just going through how the graphs look. So let's try another one. Now, I know I need my numbers 1 and 2 on the graph. So I'm going to say, okay, here's my 1, and there's my 2. And then I'm going to fill in the rest of the number line with every other number that I can. And we get something like that. Now, on my top graph, I'm going to say, hey, x is greater than 2. I'm going to put an open circle on 2 because it's not included. And I'm going to fill in values that are greater than 2, which in this case is to the right. On my lower one, I'm going to say x is less than 1. So I'm going to put an open circle on 1 and fill in portions of my graph that are less than 1, which in this case are to the left. And I'm going to draw a set of dotted lines between my barrier values so that I know what 3 sections of the graph I'm looking at. I have the left, the middle, and the right. So on my first one, my union, I'm saying, okay, does one of my 2 graphs have these values on the left boundary? Of course, the lower one does. So I'm going to include all of these values. Does one of my graphs have the values between 1 and 2? Well, neither one of them does, so I'm not going to shade in the middle. My top one has all these values to the right, so I'm going to put them in as well. Awesome. And then because these have a gap, I need boundary points. And then I have to ask, does either one of these graphs have the number 1? No, so I can't fill it in. Does either one of them have the number 2? No, so I can't fill that in. So therefore my union set, or my OR function, would look like this. With the intersection, it's a little more complicated. I need something that's in both of them. Only one has the left, only one has the right, neither have the middle, and therefore neither will have these boundaries because it's only included in the bottom one and it's not actually there. It's only in the top one, but it's not actually there. So my intersection is an empty set. There are no values shared between these 2 graphs. One's right hand, one's left hand. Nothing is in common. Awesome. Let's try a few more. So, in my top one, I need numbers from 12 and 10. So I'm going to fill in, let's see, 10, 11, and 12. 10, 11, and 12. I'm going to fill in the rest of the values with all the other numbers. So that way when I graph x is less than or equal to 12, I put an open circle, I shade in the less than, which means to the left. I also include that point because it's or equal to 12. On the next graph, I say x is less than 10. Again, I shade to the left, but this time I don't include my point, my boundary. Now that I have my two original lines graphed, I'm going to take a peek at the left, the middle, and the right sections. And for union, I'm going to say, hey, does either one of them have the left numbers? Yes. So I'm going to shade that portion in. Does either one of them have the middle? Yes. I'm going to shade that portion in. Does either one of them have the right? No. Neither one of them, like tigers and sharks, neither one of them is a planet, so I don't shade that in. Because there's no gap between the left and the middle, I include the barrier point or the boundary point. But because it stops right here, I have to put a boundary in. I'm going to say, hey, is my boundary point included in one of the graphs? In this case, yes, it's included in the top, so I shade it in. That's a union. For the intersection, I say what's in both? Well, they both have the left. I'm going to shade in the left. Only one of them has the middle, only the top one. Neither of them have the right. So because there's a boundary here, I'm going to put a circle and say, do they both have the number 10? The top one does, but the bottom one does not, so I leave it open. The next one, I need numbers between 7 and 9. So I'm going to say 7, 8, 9. And then I fill in all the other values in between. Boom, there we go. And so I know with my top one, any value is greater than 7. So I put a circle on 7. Because it's included, I shade it in. And then I also shade in the greater than values, which means in this case, to the right. My next one, x is greater than 9. Put a circle on 9. It's not included, so I don't shade it in. And I shade the greater than values, which in this case is to the right. Next up, I'm going to draw my barriers. And say, hey, I'm only looking at the left, the middle, and the right. For union, I look at the left, nope, middle, yes, right, double yes. Because they are included on both sides, I include the barrier. I put a circle because it's a yes and then a no on the other side. And I look at the point itself, and it is included in the top one. So I shade it in. On the intersection, I only include what's in both. Double no, no, yes. So I only shade in to the right. And because there's a barrier or a boundary between a shaded and non-shaded portion, I need to put a boundary so that we know it is either included or not. And I ask myself, do they both have 9? Only the top does, the bottom does not. So I stop right there. Awesome. And the last thing, we need numbers between -3 and -3. This one looks like it might be a little confusing because I don't have a left, a right, and a middle. just have a middle. Okay? Or in this case, I have a left side and a right side. Well, for the first one, I'm going to look at x is less than -3. So open circle, less than. For the next one, greater than or equal to -3. So closed circle, greater than. For the union, I ask, well, what's in either one? Well, actually, let's draw our barrier first, because there's only one barrier. And I say, yes, I have a left. Yes, I have a right. And because I have the left side and the right side of a single barrier, I go straight through. I don't actually need a point in the middle, which means I go all the way through. So again, I get all real numbers or infinite solutions. However, with the intersection, because I only have the left up top, I only have the right on bottom, I only have the middle point on the bottom, it means the intersection is an empty set. And that's it. So what we're doing today is we are practicing skip counting, or practicing our times tables up to 15. Now, the big reason why we're practicing them up to 15 is that a lot of what we do in this course is we're going to be undoing multiplication via division. And we need to be able to spot a lot of these numbers right offhand. So what I want you to do is I want you to fill out this table and say, okay, what is 1 times 1? Which is 1. What is 1 times 2? What is 1 times 3? What is 1 times 4? And now this is how the multiplication table is filled out, is we multiply each row by each column. The reason why I call it skip counting is I'm counting by ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Another way is I could say 2 by 1, 2 times 2, 2 times 3. But again, we're practicing skip counting. So to fill out this table, I'm saying I'm going to count by 2s. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, so on and so forth. If I count by 3s, 3, 6, 9, 12, 15, so on and so forth. And again, this is valid simply because we're trying to notice if I see the number 10, I know that number 10 has 2 possible factors of a 5 and a 2. I need to be able to know that right offhand. And so let's fill out this table all the way down to 15 by 15. So if I get 15 by 15, I get 225. And I can skip count backwards if I want. 15 from that is 210. 15 from that is 195, 180, 165, 150. And I noticed that by skip counting backwards, 15 times 10, well, that's 15 with an extra 0 on it, is 150. By practicing my skip counting, I am actually filling out this multiplication table. And then when you're done with this, you're going to use this table to fill out your perfect squares. When I see a number in the upper diagonal, that means that's an exponent. 1 times 1 is 1. 2 times 2 is 2. 3 times 3 is 3, so on and so forth. 5 times 5 is 25. 7 by 7 is 49. 9 by 9 is 81. If you don't know these off the top of your hand, practice your skip counting and fill out this table in order to fill in this box right here. And on the flip side, we need to know our perfect squares. When we look at square roots, we need to know exactly what 2 numbers multiplied together give me this, if they are the same number. So starting over here, it should be pretty easy. What 2 numbers that are the same number multiply together to give me 9? Well, we know that's 3. But let's say we don't remember that, or we don't know that off the top of our head. Well, again, if we fill out this table, and I practice, let's say, counting by 5s. So 5, 10, 15, 20, 25, 30, 35, so on and so forth. And I say, okay, what 2 numbers multiply together give me 25? And I'm like, let me look at my table. I'm assuming my table's completely filled out, and I say, I see a 25 here. Is it multiplied by the same number that's in the top of the column and the edge of the row? Yes, those are both 5s, which means what two numbers, if they're the same, give me a 25? 5. So we say that that is the square root of 25. If I take 5 times 5, I'll get that. If I take 7 times 7, I'll get that. And so fill out this table so that you can knock out your perfect squares and your perfect roots, and you're golden.